Hello. Today we're going to talk about those periodic trends that I was referring to on yesterday's notes. Before you get started, you may want to set up a second tab where you open this page called Periodic Trends. There are two periodic tables that have been marked up to show you what the trends are as we go through the week. So as you maybe interact with the notes or want to refer to them to help you complete your assignments, or even if you just want to mark up your own periodic table, these are great references for the rest of this week's lessons on the periodic trends. Okay, so I have provided them just at the beginning of this particular set of notes, but they are provided for you as a separate page for you to open up and look at and keep open while you go through your assignments. Okay, so let's get started today. So the first type of trend we're going to look at that's due to the periodic law because of where these valence electrons are going into the different shells is the size of an atom or atomic radii. So if we look at just the representative elements in terms of their size in picometers, and you don't have to memorize these numbers, you just have to know what the general trends are, and there are lots of exceptions. So we're only looking at what the general trend states. So if you look at the size of these elements, you see they appear to get smaller as you go across the period, correct? So they appear to be smaller as you go across a period. And then as you go down the group, they appear to increase in size, don't they? They get bigger. Okay? So we can say that going down the group, the atomic radii increases, and going across a period, the general trend is that they decrease in size. Okay? The reason being goes back to that lesson that I talked about on shielding and screening. Since electrons are being added in energy levels farther away from the nucleus, the inner electrons block the positive nucleus and repel the outer electrons. So that's why they increase in size. So that metallic character that I talked to you about, those loosely held valence electrons the other day, this is why. They are feeling a greater repulsion, therefore they're loosely held. Therefore, all these other trends occur. As you go across a period, though, each element has increased nuclear charge because you're adding the protons to the nucleus and you're adding the same shell electrons. So the shielding effect is constant, and you don't have a greater repulsion. Instead, you have a greater nuclear charge. That means the attraction between the positive nucleus and the negative valence electrons are stronger. That's why, going across a period, nonmetals tend to hold tight to their valence electrons. Here's another way to look at it. We've got some transition elements mixed in, and we got, periods 1 through 6. So you can see there's some slight variations as you go across, but if we talk in terms of a general trend, in general they decrease in size and they increase in size going down the group. This is a nice periodic table for you to look at in terms of these trends. I have an interactive periodic table also provided in the lessons for this week, and it's a website that you can go to and you can visualize these trends. So let's see if we can look at the atomic radius. So I'm just going to click on an element, and then we're going to look at just one of the properties, and we're going to look at atomic radius. So this is a scatter plot. It gives it to you in the best way. As you go across a period, see we got lithium, which is in period 2. As you go across a period, they decrease in size. You see, and we end in neon. So going across a period, they decrease, but then going down a group, they increase. Sorry, going across a period, they decrease, and going down a group, they increase. So if you want to, you can look at like a shaded ball, and that's another way for you to visualize. again, going down the group they increase, and going across a period they decrease. So that's a different way. You can look at them in different versions of the shades. You can look at a cross line. You could look at a sorted scatter, which doesn't really, it just squares the values. The scatter plot's the best way to look at it. So again, here's potassium. We're in period 4, and we go across, and you can see there's some slight variations, but the general trend as you go across a period, they get smaller, and as you go down a group, they increase. So as you connect these dots, they increase. And see, here's an anomaly, and it's because these elements, neodymium and promethium, again, they're not exact, but they are in general increasing and decreasing. Okay. Now I got to figure out how to get out of here. There we go. Okay. All right. So let's practice. Let's put this into practice. So you'll want to bring up the tab for you to look at on the periodic table trends. So if we were to get a set of elements, and I told you to put them in order from smallest to largest, how would you do that? So take a minute and you can pause and think about it, look at your periodic table, and then resume the video. So we have selenium, sulfur, oxygen, and tellurium. So if we were to put them in order from smallest to largest, we see that oxygen is smaller than sulfur, which is smaller than selenium, which is smaller than tellurium. So if you look, those are elements that are in the same group. So as you go down the group, the atomic radius increases. So putting them in order from smallest to largest gives us that order. Okay, let's look at this set of elements. So we've got phosphorus, chlorine, sulfur, and silicon. If you look at your periodic table, those are elements in the same period. So you want to pull up your little periodic table and pause the video and think about how you would order these. So chlorine is smaller than sulfur, which is smaller than phosphorus, which is smaller than silicon. So if you look at the periodic table, these are elements in the same period. And then one of the things that happens as you go across the period is they get smaller. So whether I ask for them to be in order from largest to smallest, or smallest to largest, or even if you had them mixed, like in a diagonal. Okay, so you can even look at them in terms of diagonally. If you wanted to draw lines on your periodic table in the diagonal, you know which ones get smaller and which ones are bigger. All right, the other type of trend is that of an ion, which we haven't discussed yet. So this is one introduction to the concept of an ion. We'll go into more detail next week on how ions are formed, but it has to do with their valence electrons and these periodic properties and trends that we see. Okay, so the first type of ion is called a cation, and it's a positive ion. So in terms of their size, they are always smaller than their neutral atoms. So for example, lithium and lithium ion, and sodium ion. And the reason being is because they have loosely held valence electrons, so the energy-wise it's easy to lose them rather than gain to make an octet, because remember, all elements want to gain, lose, or share electrons to have an octet. That's the magic number. So as a result, they end up having a shrinking atom, not just because they lost 1 or 2 valence electrons, but because that pull towards the nucleus is stronger. Now they have an octet, and we'll see that later when we talk about how atoms gain and lose electrons to form ions. Anions, which are negative ions, are always larger than the neutral atom, and the reason being is because you've got more electrons in the valence shell and the nuclear charge is constant, but therefore you have a greater repulsion of those valence electrons. So anions are always larger because of the repulsion of those valence electrons. So if we look at this handy little chart, we can see how this works. So the orange are the neutral, yellow are the neutral, and then the green are the cations, and then the brown is the anion. So in general, they decrease across a period, and you can see that because here's a large potassium going across even though the anions are larger, they still decrease in size. We can see that number, 0.22, 0.198, 0.196. Okay, so even though they're larger for the anions than the cations, they both decrease across the period. Okay, and then they both increase down the group. So in general, we can say that the ion size of an ion decreases across a period, whether it's the cation or anion, and they get bigger down the group. If you wanted to, you could draw a simple diagonal if you want to look at it that way. It's not wrong to do this, but you could say like this, and you could say these are the smallest, and then these are the biggest. So if you happen to be getting questions maybe that are CK12 questions where they are like mixed, then you just kind of have to high grade them and group them based on that size. Again, if we look at this particular example on this periodic table, let me turn off my laser and see if I can get my pointer back. Okay, come on, pointer. Okay, maybe I'll just go back to, let's see, I want my pointer. I just want my pointer. I want just nothing. There we go. Okay, so we're going to go back to this website, and we're going to look at ionic radii. Ionization, they may not have ionic radii. I don't see. Well, I don't see ionic radii on here. Heat ionization energies. Okay, so we're not going to look at ionic radii. I thought it was on here. I must be overlooking it. Okay, so we'll skip that part. Okie dokie. All right. So again, pull up your little periodic table where you have them labeled and put these in order from smallest to largest. We've got gallium, potassium, and calcium. If you notice in the periodic table, those are elements in the same period. So if you said gallium is smallest and potassium is the largest, you are correct. All right, let's look at these elements. We've got iodide, fluoride, bromide, and chloride. Put them in order from smallest to largest. Again, hit pause. So if you said fluorine was the smallest and iodine was the largest, you are correct.